Welcome everyone to Jules Selena's final defense. Very happy to have everyone here. I guess the way it goes that Jules will give some presentation first. And would you like questions along the way, or do you want everyone to save it till the end?
The end.
Okay, so save your question till the end. We'll open that for the audience. So welcome, Jules.
Good afternoon, everyone. Thanks for taking the time to attend my defense today. And I'm very delighted to be sharing everything I've been doing since 2014 on this wave mean flow transport of carbon dioxide in the mesosphere and lower thermosphere region. So this is the outline of my entire presentation. So I'll start off by introducing some pertinent concepts and phenomena related to my work, as well as the main issues that my dissertation helps to try and address. I'll then proceed by presenting the two main highlights of my dissertation. So obviously, I won't be able to share everything I did throughout my dissertation. I will just be focusing on the two main highlights, as well as, of course, justifying what's so important about them. I'll then end with my own recommendations for future work that build off all the stuff that I did for my dissertation. So to introduce the mesosphere and lower thermosphere region. So where is this? So this region is between 80 and 110 kilometers. In our atmosphere. It is a region with some actually very, very peculiar characteristics in that, so first, the coldest region of our atmosphere is actually in this region. Now, even more peculiar is that this region actually occurs over the summer hemisphere and not the winter hemisphere, a region that we call the cold summer mesopause. Second, the longitudinal differences, and therefore day-night differences, here in this region are actually also quite massive. So here in the surface, so say here in Taiwan, for example, day-night differences, 10 degrees is already considered high. So in this region, day-night differences can reach as high as 30, even 50 degrees. The chemical structure of this region is also very complicated because it is a significant mix of neutrals, ions, and electrons. Now, the mechanisms that drive the dynamical and chemical structure of this region are the same mechanisms that actually make the MLT region a bridge between the lower atmosphere, which contains all our weather phenomena, and our upper atmosphere. Now, in the mid-2000s, our advances in observational capacity have allowed us to see that the upper atmosphere is actually not just driven by what one would typically expect, solar and geomagnetic phenomena. It was found that phenomena like tropical convection, which we know is the one responsible for rainfall, hurricanes, typhoons, was also found to significantly perturb the upper atmosphere. And it is because of this that we are now required to look closer at this coupling between the lower atmosphere and the upper atmosphere for us to monitor and keep safe all of our space-based technologies. Now, on a given day, it's very easy to take this responsibility lightly because we can hardly really feel the importance or the problems on our space-based instruments. However, it's very important to remember that there are instances where such problems can have very, very dire consequences. So what my dissertation does is it tries to look closer into how the lower atmosphere and the upper atmosphere couple each other by looking closer at this very region. In particular, my dissertation looks at two main issues in this region. The first one is on diffusive transport due to breaking gravity waves. So diffusion is just one of two main categories of transport processes in the region. So diffusion is the transport of chemical species from a region of high concentration to a region of low concentration due to very, very small scale random motions. Now we can already do a fairly good job of simulating this transport explicitly. However, for us who are really after simulating the entire global atmosphere, simulating these very, very small scale motions as well as a myriad of other motions in our atmosphere can be very, very computationally expensive. A common alternative that is used is a formulation based off of shear theory, where the diffusive transport is parameterized by a coefficient called the diffusion coefficient. And so to simulate diffusive transport in our atmosphere using this formulation, the goal is really just to find this accurate diffusion coefficient. Now in the MLT region, there are two main or dominant diffusive processes. The first one is molecular diffusion, which is just diffusion typically driven by the background temperature and the molecular weight of chemical species. Now the diffusion coefficient from this is easily accounted for through laboratory experiments. The other main diffusive process in the MLT region is the one called eddy diffusion, and this is the one driven by turbulent motion, which in the MLT region is predominantly due to breaking gravity waves. In contrast to molecular diffusion, eddy diffusion coefficients are very, very difficult to get, and they continue to be a major source of error in our simulations of the middle and upper atmosphere, of the entire atmosphere. So, but what are gravity waves? First, so gravity waves are oscillations in our atmosphere that are brought about by the horizontal or vertical displacement of air from its equilibrium position. Now, on a fine day, these gravity waves can actually manifest as nice cloud patterns like these, or in our plane rides, they manifest as our unwanted clear air turbulence. Now, it's very easy to think that, well, we don't really see this often, and while this is big compared to the global atmosphere, it's still small, and again, we don't really see them often, so it's easy to think that, okay, maybe these gravity waves don't even occur as much. Actually, these gravity waves are so important to the MLT region because while they do originate here in the lower atmosphere, so in things like flow of air over the mountains, that's a major source of these gravity waves, while they do source here in the surface, they're actually capable of propagating up all the way up to the mesosphere and lower thermosphere region, where they break and they cause what I mentioned earlier, the cold summer mesopause. Now, getting the eddy diffusion coefficients from these gravity waves is very difficult, and this is immediately evident by the formulation used for this. So, a common and fairly reliable formulation is the one by Richard Lindzen in 1981, where his formulation accounts for the vertical propagation of the wave all the way to the MLT region where it breaks, and then its damping is parameterized by this eddy diffusion coefficient. And so from this formulation, we said it's related to things like the horizontal wave number of the wave, the background winds, the phase speed of the wave, the Brunt by Sally frequency, scale height, zonal wind, and so on. Now, unfortunately, this formulation was derived using ground-based local observations. We are still unable to validate this globally. To be able to do that, we need satellite observations that actually capture all of these parameters. Unfortunately, right now, we're just unable to fully get that. And so from this, we see that for the first issue, diffusive transport due to breaking gravity waves, the main problem that my dissertation tries to figure out is finding a way to get these global mean eddy diffusion coefficients due to breaking gravity waves. So the second issue that my dissertation tackles is on advective transport due to atmospheric tides. So advection is just the other main group of category of transport processes. So this is the bulk transport of chemical species by wind. So if winds are moving northeast, the species move northeast. Now, in contrast to diffusion, this one can be explicitly simulated since it's quite large. It pertains to large-scale phenomena, and the formulation is typically through this continuity equation. Now, my dissertation is specifically interested in advective transport due to atmospheric tides. Now, what are these tides? So these tides are oscillations in our atmosphere with periods that are harmonics of a solar day. I mentioned earlier the day-night differences, the massive day-night differences in this region. These tides are actually the ones that predominantly drive the very, very massive day-night differences. In fact, they not actually only manifest as temperature differences, the massive temperature differences. They actually significantly affect the dynamical, chemical, and electrodynamical structure of the MLT region and the upper atmosphere. Now, these tides are either forced in situ or they originate from the lower atmosphere. These lower atmospheric tides are actually the ones now responsible for what I also mentioned earlier, how tropical convection affects the upper atmosphere. And so from that, we see just how important knowledge of these tides are. Now, most of our studies, global studies right now on the global variation of tides is based off of temperature observations. And with that, we were already able to know a bit more on when and where these tides really are very strong. We were also able to determine a bit of dynamics behind the MLT region from that. However, these observations are not enough to be able to give us an idea of advective transport due to atmospheric tides. So two main issues, two problems that my dissertation deals with. The first one is on diffusive transport due to breaking gravity waves. The problem is finding a way to get these global mean eddy diffusion coefficients due to breaking gravity waves. The second issue on advective transport due to atmospheric tides. The problem is finding now a way to observe these advective transport processes that are driven by these atmospheric tides. So what my dissertation tries to do is try to knock out these issues by suggesting the use of satellite observations of a tracer called carbon dioxide. So carbon dioxide, I'm sure everyone knows here, is more notably known for its very, very important role in global climate change. Below 15 kilometers, the predominance of its IR absorption causes our very, very well-known global warming. And above 15 kilometers, the predominance of its IR emission causes this global cooling. Now in the MLT region, CO2 is not just responsible for global cooling. It is actually also a very, very important dynamical tracer for a very, very wide range of dynamical motions because its photochemical lifetime is approximately 1,000 days. And well, we also know that this is also the reason why removing CO2 from our atmosphere is very, very difficult. So this dissertation specifically uses carbon dioxide observations from an instrument called the sounding of the atmosphere using broadband emission radiometry on board the thermosphere, ionosphere, mesosphere, energetics, and dynamic satellite. Now, much credit to the team, the SABRE team, for wrestling with this very, very difficult problem. This problem is evident with how this is actually a data that was only publicly released in 2016, and I'd like to really acknowledge our main collaborator for this, Professor Jia Yue of Hampton University and the University of Maryland, for giving us early access to this data as early as 2014, when he gave us the responsibility of coming up with cool stuff from this data. Also, the difficulty in this problem is evidenced by how actually we currently only have daytime data here. So the problem really here that needs to be wrestled with is getting CO2 volume mixing ratio from infrared limb measurements. So right now we've only figured out for daytime and we have yet to deal with nighttime. So with this data, the two main objectives of my dissertation is first to derive global mean eddy diffusion coefficients from SABRE carbon dioxide observations, and also from the same observations we're going to try and infer the local time variations of effective transport. So for the first highlight, is really deriving now these SABRE CO2 derived eddy diffusion coefficients in the MLT region. So how did we derive these coefficients? So first we took SABRE CO2 profiles between 50 degrees south to 50 degrees north and calculated bi-monthly global mean profiles from February 2002 to December 2015. We then simulated each one of these profiles using a one-dimensional photochemical and transport model. In our simulation, we first set the vertical wind in the model to 0. This we can do because we calculated the global mean, and so we effectively canceled out the large-scale vertical advection. Then we set the model's CO2 lower boundary to be consistent to that of SABRE, and then we adjusted the eddy diffusion coefficient in the model until we minimized the observed and simulated CO2 profiles. So here now are our global mean CO2 profiles from SABRE from February 2002 to December 2015. This is the one that's simulated, and as you can see, they're actually quite close, and the similarity is confirmed when we took the percent differences between them, and we found they are within 2% difference of one another. These now are the eddy diffusion coefficients that we derived from the simulation of these CO2 profiles, and this is the first highlight of my dissertation, which is the first ever satellite-based global mean eddy diffusion coefficients that spans more than one solar cycle. So now we use these coefficients to answer two important questions on the issue of diffusive transport due to breaking gravity waves. The first question is, what are the impacts of the seasonality of global mean lower thermospheric eddy diffusion due to breaking gravity waves on the seasonality of the ionosphere and the thermosphere? To answer this question, we first need to show that our coefficients that we derive from CO2 are similar to the coefficients that were calculated from Lindsen's gravity wave parameterizations in three-dimensional models. So the models that we use are first the specified dynamics cold atmosphere community climate model, which is a model that is able to simulate the atmosphere from the surface all the way to 140 kilometers. This model is also constrained by observations from the surface all the way up to 50 kilometers, thereby making its simulation of the MLT region fairly reliable. The other model is an upper atmosphere model called the thermosphere, ionosphere, mesosphere electrodynamics general circulation model, time PCM. This model simulates the atmosphere from 30 kilometers all the way up to 500 kilometers. So here now I show the comparison of our coefficients with the coefficients from these two models. So this one in blue is the one so this is the seasonality of it, so from January all the way to December. So the one in blue is from our coefficients, the one in red is the one from SD Wacom, and the one in orange is the one from time GCM. This is presented as percent differences with respect to their mean. So Sabre has a mean of 41.31, SD-WACAM 50 around 60, time same is 42. It's important to note that when comparing these coefficients, because of just how difficult they are to derive, and also with some sensitivity studies on what their variance would mean in terms of how they affect the overall dynamics, saying that the coefficients are significantly different typically mean at least an order of magnitude different from one another. So say Sabre is 41, for it to be different from all these three, it should be at least 140 and above for it to be different. And so from this, the similarity in the means and the overall variance throughout the year, we can say that our coefficients are consistent with those from gravity wave parameterizations, which allows us to say that our coefficients can be attributed to breaking gravity waves. So now that we were able, from that we were able now to say that our coefficients may be attributed to breaking gravity waves. We now take those coefficients and then plug them in an another upper atmosphere model called the thermosphere, ionosphere, electrodynamics general circulation model. So this model simulates the atmosphere from 97 all the way to 500 kilometers, and conveniently its eddy diffusion can be manually specified. So we just take those coefficients and plug them into the model and see how it simulates the seasonality of the ionosphere and the thermosphere. In so doing, we also are able to validate this eddy diffusion hypothesis, which suggests that the seasonality of the upper atmosphere requires three things. The first two are what we would expect, solar and geomagnetic phenomena. But here, this hypothesis suggests that maybe the seasonality in eddy diffusion due to breaking gravity may also be needed, may also be the final final unknown forcing that would allow us to simulate the seasonality of the upper atmosphere. So here now I show the results of our simulation. So in orange is the one so this is thermospheric neutral density. So this is an entire year. So again, this is seasonality. So orange is the one that's driven by our coefficients. The one in red is the one that is found to be consistent with what is observed. And from this, we see they're quite off. And so from that, we say that, no, our eddy diffusion coefficients cannot simulate the seasonality of neutral thermospheric density. The same can be said of ionospheric electron density. So this is F2 peak electron density. This is its height. So this is the one that's consistent with what is observed. This is the one that we simulate, and as you can see, they're also quite far from what is observed. And so also we say that our coefficients cannot model the seasonality of the ionospheric electron density. And since we show that our coefficients may be attributed to breaking gravity waves, we can now answer the first question. Eddy diffusion due to breaking gravity waves in the lower thermosphere is not needed to fully force the seasonality of the ionosphere and thermosphere. So this is the main conclusion of our 2016 paper, and we were very pleased to find that these succeeding papers all supported our conclusions there. Now on this first question, we delved more on the seasonality of these coefficients. And the second question, we're now going to take advantage of one very important novel characteristic of our coefficient, which is that it spans even 2 years more than a solar cycle. We will do that. We'll take advantage of it now to answer this very, very important question. What are the solar cycle responses of lower thermospheric eddy diffusion during austral winter? Now, why austral winter? So when talking about solar activity, it's easy to immediately just think of temperature responses. High solar activity, warmer temperatures. Low solar activity, cooler temperatures. Here, we're not just after temperature responses. We're actually more interested in finding out if there's a solar cycle response in the motions in our atmosphere. Specifically, our work here is aimed at finding if there's a solar cycle response in lower thermospheric eddy diffusion. And we look at austral winter because it is in this season where past observational and simulation studies have already started to show that there is a response in the dynamical motion, like wind, for example, in the stratosphere and the mesosphere. So our work here is just building off of that to now see, well, since the lower thermosphere is just above the mesosphere, maybe there's also a response just above that. So here now I show first the solar cycle response of Sabre CO2 in June. So every data point here is say June 2004, 2008, 12, 14. So this is June CO2 in the lower thermosphere at 97 kilometers from June 2002 all the way to June 2015. So this is overplotted with the F10.7 index, which is an index for solar activity. And we see here that during years of low solar activity, we have high CO2. And on years of fairly high solar activity, we have lower CO2. Now this is just consistent with what we know of the photochemistry of CO2, which is that it's dominated by photodissociation. Now from this, we were able to derive these eddy diffusion coefficients now, also in blue, overplotted by F10.7. So again, each data point here is eddy diffusion in, say, June 2004, 2010, 2014. So this is June eddy diffusion in the lower thermosphere from June 2002 to June 2015, and it's overplotted by F10.7 index. And we found that during solar minimum, there is an increase in eddy diffusion, and during solar maximum, there is a decrease in eddy diffusion. Now, we were surprised to find something similar also in the SD-WACA model that I mentioned earlier, which was ran for 3 solar cycles. So, by the way, this is all global means, so between 50 degrees south and 50 degrees north. So here we were also able to find that during solar maximum, there is this decrease in eddy diffusion, and during solar minimum, there is slight increase, although the most dominant response is really a drop in solar maximum. So with that, we were very curious, and we're now going to try and we tried to explain it. And so I'll now present what are the mechanisms that could possibly be driving this. So again, this is global mean, and it involves looking at it pretty much involves the solar cycle response of eddy diffusion between 50 degrees south to 15 degrees north. So to be able to explain that, we need to look at the responses from 50 degrees south also to 50 degrees north, and we were surprised to find that between those 2 latitudinal bands, the response is negative, and it's highlighted by this very, very strong negative response in 40 degrees south to 20 degrees south. So this is regression coefficients between eddy diffusion and F10.7. So negative response also means that during solar maximum, eddy diffusion is lower. During solar minimum, eddy diffusion is higher. And so this one is what it shows that it's consistent with what we showed, the time series that we showed earlier. However, we made sure, because when working with linear regression, it's that will typically always tell you something, but sometimes it's not really there. So we made sure to check the time series if it really is actually there. So that's what we show here, and yeah, we were surprised to find that yes, there does seem to be this drop during solar maximum and slight increases in solar minimum. So now, to complete the story, I'm going to show the mechanism that we found for this one. However, I will not show the mechanism as a bunch of plots because it's really a lot of detail, and in the interest of time, I just won't be able to do that. To those interested, this is published in our recent paper, so the details are there. However, I will just present, and of course, to those really interested, I can always answer that question later. But just to cut the time, I will show the mechanism that we found as a visualization. So, because I will show here that the mechanism involves very intricate coupling of the atmosphere from the stratosphere all the way up to the lower thermosphere. So this here is pretty much the climatological mean of our atmosphere from the stratosphere, mesosphere, and lower thermosphere in June, so austral winter. So austral winter means it's winter over the southern hemisphere, and it's summer over the winter hemisphere. So this is the zonal winds that manifest during the season. So in the stratosphere, we have an easterly wind. In the winter hemisphere stratosphere, we have the westerly jet. In the mesosphere, as a result of filtering of gravity waves, you have opposite, so easterly here, westerly here. And in the lower thermosphere, also as a result of, this one is actually a more recent discovery, there's also an opposite wind pattern, so it's easterly here and westerly there. So this is the equator. And then just the circulation that happens is in winter, so the stratosphere to the mesosphere, we have an upwelling in the summer hemisphere, and it goes from summer to winter, and then downwelling here. Above that, we have this, again, is newly discovered, a winter to summer circulation. So what did we find? So what's going on during solar maximum in contrast to solar minimum that's causing what we showed earlier, the decrease in eddy diffusion? So first we found, over the summer hemisphere, there is an enhancement in ozone. This enhancement in ozone induces an increase in the latitudinal gradient of temperature. That increase in gradient strengthens the westerly jet over the winter stratosphere. With that strengthening of the westerly stratosphere jet, we get reduced westerly gravity waves. This is because gravity waves are only able to propagate past regions where the background winds are slower than the gravity waves or have a phase direction that is opposite that of gravity waves. With this reduction in westerly gravity waves, we get an enhancement in the easterly jet in the mesosphere. Now, up to this point, everything we found here is actually shown to be similar to what's already suggested in past studies. What our study here adds is that apparently this mesospheric jet anomaly extends all the way up to the lower hemisphere. And along with that, we get the reduction in eddy diffusion, which is due to the reduction in westerly gravity waves. So for this second question, what are the solar cycle responses of lower hemispheric eddy diffusion during Oslo winter? So we found that eddy diffusion is reduced during solar maximum as a result of reduced vertical propagation of gravity waves. So this is the main conclusion in our recent 2018 paper. So for the first highlight, it's really just deriving these very new first ever satellite-based global mean eddy diffusion coefficients that spans more than one standard solar cycle, and taking these coefficients to provide us with these new insights on seasonality of eddy diffusion due to brain gravity waves and its impacts in the ionosphere and thermosphere, and also determining the solar cycle response of these eddy diffusion coefficients. We now proceed with the second highlight, which pertains, of course, to the second objective of my work, which is to infer the local time variations of advective transport from the local time variabilities of Sabre CO2 in the MO2 region. So to do that now involves the work we did involving presenting for the first time that there is a significant local time variation in Sabre CO2 and explaining what drives these. So when working with local time variations and tides in general, it's always important to check the sampling of your profiles to make sure that you will get a good local time coverage over what region you're looking at. So we targeted equinox and the tropics because we know that equinox and the tropics are the seasons and is the season and region where past studies have shown tides are very, very strong. So we checked the sampling and we did find that for our purposes we can use Sabre CO2 to look at the local time variation of Sabre CO2 or of CO2 in the mesosphere and lower thermosphere region. So here now I show the local time variation of Sabre CO2 in March equinox in the mesosphere between 80 to 85 kilometers. So this is latitude and local time. And we find that just focusing on the general structure which means what goes on in morning and afternoon, because remember this is only daytime, we do find that in the morning there is low CO2 and in the afternoon there is high CO2. This is now in the lower thermosphere at 95 to 100 kilometers, and we also find that it's lower in the morning and higher in the afternoon. Now we're going to try and explain this using now simulations from another model called the whole called WACOM. The same WACOM earlier, but this time it's WACOM extended, which is a whole atmosphere model that simulates the atmosphere from the surface all the way to 500 kilometers. So here I show now its simulation of the local time variation of CO2 in the mesosphere. So we also see a general structure of weaker CO2 in the morning and higher in the afternoon. In the lower thermosphere, though, it's quite off from what is observed. So we get a peak in noon, a minimum in noontime, and it's all quite much lower than what Sabre is showing. Fortunately, though, that this disparity is not enough to really hinder us from using the model to, at the very least, just determine what are the advective processes or the processes that drive these, because that will still aid in the eventual improvement of the model to try and determine what process in the model needs to be improved to be able to correct this. So we're now going to determine or diagnose the model and determine what are the processes that drive the local time variation in CO2 in this region. So to do that, we're going to do a tendency analysis involving the three-dimensional continuity equation. So what this analysis does is that we determine the contributions of zonal advection, meridional advection, vertical advection, eddy diffusion, and molecular diffusion to the overall variation in CO2. So here now, so this is in the mesosphere. So this is the local time variation of CO2 in the mesosphere assimilated by WACOM X. And it's the same as the one I showed earlier, but now shown as a time derivative. This is the contribution to that of zonal advection, meridional advection, vertical advection, eddy diffusion, and molecular diffusion. First, comparing the advective processes and the diffusive processes, we find that the magnitudes of the diffusion processes, so plus minus 0.1, plus minus 0.01 for molecular diffusion, are quite lower compared to the advective processes, which are +-4, +-2, +-0.4. So we can immediately remove the diffusive processes as dominating mechanisms. Of the three advective processes, we find that zonal advection is also quite weak. So we're left with these two. And from these two, we find that vertical advection does capture most of the variability between 20 degrees south to 10 degrees north. However, above that, we find that we needed meridional advection. And so from this, we can argue that the local time variation of CO2 in the mesosphere may be predominantly driven by meridional and vertical advection. And since we showed earlier that there is at least the general structure is captured by what's observed, we can at least infer that the local time variation of meridional and vertical advection may be similar to what is being shown in Wacom X. If not, maybe slightly, it needs just a slight enhancement. In the lower thermosphere now, so again, this is the local time variation in CO2 shown as a time derivative. So this is the contribution to that by zonal advection, meridional advection, vertical advection, eddy diffusion, and molecular diffusion. Similar to the mesosphere, we found that the magnitudes of the diffuser process are quite weak, so we can remove that. Now, of these three, the only thing apparent is before noon time, vertical advection is really, really needed to force this one. Now, which of these two is important? So it's not as apparent as I showed in the mesosphere, but we did the calculations of combining them, and then we also found that it's meridional advection and vertical advection that drives most of this. And since we showed earlier that Wacom X cannot even capture just the general structure of what is observed, we still probably need to really modify the model's meridional and vertical advection to be able to infer something about their local time variation. Now, presenting and explaining those local time variations CO2 for the first time not just allows us to infer some idea of the local time variation in advective processes. This presenting and explaining these for the first time actually also allows us to answer two very, very important yes-no questions on the topics of climate change calculations and temperature retrieval algorithms in the region. So the first question, should local time variations of CO2 in the MLT region be accounted for when calculating long-term trends in the region? Now this question actually stems from some recent work showing that the trend of CO2 in the lower thermosphere is much faster than the one at the surface. Now we know here in the surface, the trend of CO2 is 5 to 6% per decade. In this recent study, it was found that the trend is actually reaches up to 10% per decade above 100 kilometers, which is quite high. A more recent study, though, showed that this was just a result of not being able to really look at the sampling of the data and calculating from this. Now, this sensitivity and the sampling of the data suggests something that's never been suggested before or determined before. Is there a local time variation in CO2? And as I just showed, yes, there is, and we're able to explain it. And so from that, we're able now to answer the first question that yes, when calculating these local time variations, especially using SABRE CO2, we need to carefully account for the sampling of the data for it to be accurate. So for the first question, so yes. The second question now pertains to temperature retrieval algorithms in the MLT region. So this question stems from instruments like SABRE, whose retrieval algorithm has a dependency on CO2 volume mixing ratio. Here I show the local time variations of temperature using temperatures that are derived from a retrieval algorithm that does account for the local time variations in temperature. This one is the local time variation of temperature, so this is mesosphere, lower thermosphere. Also from SABRE, but from a temperature that was derived using a retrieval algorithm that does not account for the local time variations in CO2. And we took the percent differences, and we found that there's up to plus minus 10% difference between the two, which is actually quite high when talking about tidal dynamics, and most importantly, when talking about calculating accurate trends in the MLT region. And so for the second question, yes, we need to account for such local time variations. So again, the highlight of the second highlight was really just presenting these for the first time and explaining them, the local time variation in SABRE CO2. And with that, we're able to infer some ideas about the local time variation of advective transport processes, as well as answer these two very important questions. So in summary, So for our first highlight, again, it's really just deriving those eddy diffusion coefficients, and in deriving those first ever satellite-based global mean eddy diffusion coefficients that spans more than a solar cycle, we were able to provide these two new information. The first one on the seasonality of eddy diffusion due to brain gravity tubes and how they impact the ionosphere and thermosphere, and also get some idea as to what could be the solar cycle response of lower thermospheric eddy diffusion. The second highlight is presenting and explaining for the first time that there is a significant local time variation in CO2, and with that we were able to infer some idea of the local time variation of some effective transport processes, although of course a lot of work still needs to be done to be more exact as to what those local time variations are. Apart from that, we're also able to provide this very important information or yes or answers to yes and no questions. One, that yes, we need to account for the significant local time variations because it's there on calculating long-term trends of CO2 and also our temperature retrieval algorithms. So my recommendations for future work. So I showed earlier that we compared our eddy diffusion coefficients with coefficients from the Linsen gravity wave parameterization. So that parameterization is fairly well known, it's fairly commonly used, but there are other gravity wave parameterizations that try to account for more gravity wave variability. So like Heinz 1997, this one tries to account for the Doppler spread of the wave with respect to the background wind. The Egit et al. 2011 parameterization tries to account for the impact, tries to allow the gravity wave to propagate all the way up to the ionosphere and thermosphere. And so I definitely very highly recommend taking those coefficients and comparing them with these other parameterizations, because I'm sure they will provide more insights on how gravity waves really impact the MLT and the upper atmosphere. Second recommendation on the first highlight is, so we've looked at, so again, the data is 13 years long, and we've looked at seasonality and of course the solar cycle, which are fairly apparent. And but of course, I'm sure there are other variabilities there just waiting to be seen, waiting to be discovered. And so I highly, of course, recommend doing more in-depth time series analysis on these coefficients. And the final recommendation for the first highlight, we looked at the solar cycle response in austral winter. Of course, there are other seasons, and so it's I highly recommend looking also at what goes on in those other seasons. On the second highlight of the local time variations in Sabre CO2, so I showed that we have some problems with how we simulate the local time variability of effective transport processes, which before could not really be suggested because we just didn't have the data to really show that very well. Now that we have, it's important now to determine what are the consequences of such underestimations in simulating the overall ionosphere and thermosphere region. And of course, I highly recommend analyzing also the local time variations in the other seasons. So Sabre is still in orbit, and it's very much on track to provide us with a very, very novel, up to 2 solar cycles long data. With what we've done so far, so my data is only daytime, you have yet nighttime, so clearly that's a very important limitation in our work. Yet we were already able to provide some new information on those things. Clearly the best is yet to come with this one, and so I myself am excited to know what future work can be built off of what little work we've done so far involving this observation. And I'd like to end by acknowledging the very, very important teachers throughout my PhD life. The first one, of course, are my co-advisors and committee. So my first advisor, Ben, who's here right now, I'd like to thank him for guiding me during my first year and making sure, first few years, and making sure I'd be put on the right spot where I could really do well. I'd of course like to acknowledge my co-advisor, Professor Danny Young, and the committee for their time, and also for providing me with important guidance 3 years ago during my proposal that shaped everything I did here. I'd also like to thank these professors who aren't here, who are in the US. First one is Professor Jayo, who is really our main collaborator, co-author for all of these work. Despite being quite far, he never really fails to provide me with his time, and I know how busy of a scientist he is, yet his time is always ready to assist me. One of the really important things that he was able to provide me is with an opportunity to work in NCAR, High Altitude Observatory, last summer with Professor Ying Chen. She I'd like to thank her for, of course, her guidance while I was there and continuing to support me and giving me the resources to do pretty much everything I've done. So all of those models I mentioned, 3 of them are from them over at HAO. I also like to acknowledge Professor Jai and Lee. She was the one who really helped us in the solar cycle work, providing us important insights on what best approach to take that study. I'd also, of course, like to thank the heads of the satellite teams that I worked with. So, of course, the SABRE team, headed by Professor James Russell and Marty Malinzak of NASA LARC, and Professor Dong Wu. I didn't show the other satellite here, the microwave limb sounder on board our satellite, and he's one of the heads there, so from Goddard. So I'd like to thank them, of course, for providing such data. And of course, last but not least, my advisor, Professor Lauren Chang, for guiding me and really not just teaching me the science of what I've done here, but really guiding me into how to be a scientist. So, and he does it through example and through doing things like this. So, thank you, sir. And yeah, thank you.
Thank you, Ju, for a wonderful presentation. Is there any question from general audience?
I'm not from the space science field, so I'm just wondering if the future satellite advancements, like making the data more refined or in high resolution, would your results be changed, or it would be beneficial for you to have like a high resolution because you are doing like the global mean thing? So.
Definitely. Here we looked at the global mean, but we do, it's actually not so much the satellite for looking at, say, the other latitudinal variation. It's really just taking the model and switching and deriving those coefficients from that, which is a little trickier if you're not doing global mean, since you have to account for things like vertical wind and the other winds and make sure they're accurate. And on that, it would definitely benefit if we had data that's also reliable in getting us a vertical wind to be able to derive the coefficients in the other resolutions.